My name is Yahya Tawil. I'm from Hassan Khalil University in Gaziantep. I hold a master's degree. And today I'm going to present our work, a hardware implementation of an open source Qibla direction finder with tilt compensation using 9 degree of freedom, IMU, and GPS. The outline of the presentation will be, first of all, I will explain the problem statement, what the thing that we are trying to solve in this paper. The contribution we did in this paper regarding the problem, and then I'm going to present our proposed system. Basically, it will consist of three main topics: how we made the calibration of magnetometer regarding soft and hard iron distortions, and then how we calculated the pitch and roll, which is used in the tilt compensation, and finally the experiments we did. Finally, we're going to talk about the conclusion and discussions. So as you know, like all Muslims perform prayers toward the Qibla, which is the direction to Kaaba in Mecca. Like previous studies did not discuss, first of all, the compass calibration, specifically the hard and soft iron distortions, and uncalibrated compass will for sure prone to error. And according to the second thing is the tilt compensation. Previous studies also assumed running their devices on flat surfaces, which is not the ideal case. It's the ideal case, not the practical one. And according to our experiments, there would be like an error up to 100 degree for only 30 degree pitch for any handheld device. And another study, they proved that only 1 degree error in Qibla would result 105 kilometer displacement of Kaaba. And that was in Indonesia, Jakarta, the capital. In our proposed system, we have like hardware implementation. We investigated both the tilt compensation and the compass calibration. We used out-of-the-shelf 9 degree freedom IMU, which include accelerometer, gyroscope, and magnetometer. And also we added an optional GPS, and we are going to explain why it's optional. So the contribution in summary is studying the effect of having an uncalibrated compass, and proving how much important to have tilt compensation in Qibla direction calculation. The device model would be like something like the figure in this slide. Any handheld device can have a tilt, especially roll and pitch. The pitch is the angle on the y-axis, and roll the angle on x-axis. So first of all, how Qibla is calculated according to spherical trigonometry mathematics. The equation, as seen here, depends about the longitude and longitude about Kaaba, which is known, and longitude and longitude of the place where the prayer is. Also, there would be like a post-processing, like small conditions need to be discussed after calculating the Qibla. It depends if it's north or south, and also the longitude and longitude regarding the Kaaba's ones. For example, here's we calculated, for example, the Qibla for Gaziantep. After substitute the longitude and latitude, it's 8.4, but we need to check the condition number 3 in this table. So the last result is 171, which is correct. Now, to calculate the azimuth or the direction in degree, we need to use magnetometer, and the magnetometer report to us like the components of the geometric magnetic field. Calculating the direction would be as simple as arctangent hy over hx plus d, and d is the something called declination, and declination due to the fact that the North Pole, the geographic North Pole, does not match with the magnetic pole of the Earth. I mean, like the geographic north does not match with the magnetic north, and this is called declination. And calculators are used, there's a calculator based on world magnetic model for the Earth, and it's updated periodically because this declination changes from time to time periodically. It is like as simple as you enter the longitude and longitude of your place, and you will get declination. And that's why the GPS is optional, and that's why also when we use, for example, Android application for Qibla determination, they ask us to turn on the GPS. The complete process of our proposed system is, first of all, we do the soft and hard iron calibration. We will see how. Then calculating the pitch and roll angles, which are used in the tilt compensation. And finally, we will see the experiments we did comparing our calculated Qibla direction with other reference Qiblas. So first of all, the compass calibration suffer from, the compass calibration need to be calibrated to two things, the hard iron and soft iron. Hard iron is due to the materials that emits by itself magnetic field and make a distortion for the readings. And this distortion is in terms of having offset from zero. The soft iron is from materials that has high permeability, magnetic permeability, which affects about, if we can see this figure here, the ideal case is to have the readings from the magnetometer, and here is like the relation between x and y, y and z, and z and x. It's a correlation between each two axes. The ideal case would be like this red circle without having soft iron. With having soft iron distortion, it will be something like this eclipse here, the green and the blue one. And distortion is not similar over all axes, depends about the environment. That's why sometimes we need to make recalibration, depends about the environment. And the other hard iron distortion is, as you can see here, even for this circle, red circle, which is x and y relation, it's shifted from zero. So if we want to make the calibration, the hard iron would be as simple as having a three-element matrix, which correct the offset. The soft iron calibration is more complex and need special treatment of these points, and we need to fit these points under shapes circle. It is a matrix 3 by 3, and we used 4 to 10 element matrix version eigen decomposition way. If we want to discuss like in more simple way, like we can see here this plot, like the signal from a single axis from magnetometer should shape a sinusoidal signal, but as we can see here, for example, for y-axis, it's not ideal. That's because the soft iron it made this distortion, and also for x-axis, it is sinusoidal, but it's offset. It has an offset from zero. Next is the calculating of pitch and roll, which will be used in tilt compensation. Pitch and roll has multiple ways to calculate. We used complementary filter to combine between accelerometer and gyroscope. Actually, having using the accelerometer to find the tilt in terms of roll and pitch is very noisy. Here's the blue line. It's very noisy and spiky. And this is due to the fact of how the accelerometer itself works. It's very sensitive to noise, so you can see how the spikes have a very huge margin between values, so it's not suitable. Then we tried to use the low pass filter. It's better, but still has like some jitter, spiky. Gyroscope is also like the green line is good, but and has less effect of noise. But unfortunately, it has like accumulated shift over time. So the best solution was to use complementary filter expressed in this equation, combining both of the sensors to find the pitch and roll angles. In this slide, like this is like how we made the tilt compensation. Like actually, the device has like roll and pitch angle. So what we are trying to do is to emulate like the device is really on flat surface. So we need to first of all bring back the roll angle and bring back the pitch angle. So we have like two rotation matrices, one for the rotation and one for pitch. And there are more details in the paper, how we calculate them. And this is the final matrix. X and Y and Z are like the components from magnetometer. After the tilt compensation are here, and here are the values before compensation. And just to express how important to have the tilt compensation, here is, for example, for gas in-tap situation, the Qibla here is 171, as we saw. And this line is the one purple is our method. The one in orange is using the very simple way previous works used, using the equation of arctangent plus the declination. And here like the three angles of pitch, roll, and yaw. As we can see here, whenever we have like a pitch angle as small as 30 degrees, we can see here error can reach up to 100 degree, which is huge. So that's why tilt compensation is very important. This is like a small. So this is for first prototype, like before it's been like handheld device, and it's compared with Qibla Finder from Android application. It's printing here Qibla on the screen. You can see like I'm moving here with extreme pitch and it's still stable. The second prototype here, I used Arduino Nano. We used Arduino Nano 33 BLE with this device. And as you can see here, now it's 170. It's going to be 170 something. It will print GABA, and you can see here I will make a pitch. Yeah, so this is basically the prototype for this paperwork. This is another experiment in terms of table. These are like 4 tests, different tests. Each test has like a reference direction and a different setup for pitch and roll, 4 different setup for each column. As you can see here, for uncompensated direction calculation, it's has like a huge error. It here like it should be 257. You can see like there is sometimes 100 degree error. But as you can see here, for after making the tilt compensation, it's almost steady. So on average, it's reported it's plus and minus 5 degree error only when we make the tilt compensation. We made
Can we speed up, please?
Yeah. I finished actually. Just like here, I show like 2 experiments comparing with Android application, Qibla Finder, and inside the mosque, 2 mosques. So as a reference, Qibla. So the conclusion or the future, let me skip the conclusion. The future work would be adding a mechanism to know exactly when we need to redo the calibration, depending on the plots I presented. Also, we should also embed the calibration process on the device itself. Currently, we are using a PC tool to calculate the matrices, calibration matrices. And finally, using another representative formula for pitch and roll and yaw, which now we are using Euler formulas, but the better one is Quaternion, which is more steady and does not suffer from something called gimbal lock. And this gimbal lock is something very known for Euler formula. This is the ending. Anyone interested, the source files is published in this repository, GitHub repository, and thank you all. If anyone has any question, please ask me.
Thank you for your presentation. Yahya, can you speak Turkish?
Not very well, actually.
Okay.
I'm sorry.
Okay. I want to ask one question.
Sure.
Is there any other application or implementation of these device for finding anything except Qibla?
I mean, I believe this is not something new. I believe this is in robotics, for example, something very used, having the tilt compensation. But actually, in the depending on the literature review, none of the previous works discussed this. But basically, this work can be utilized in any other application, because basically Qibla is just a direction. You can implement this in a robotic application, for example. Nothing will prevent you. You can define your own target direction. In our case, it's Qibla, but for robotic, it can be any angle. So I think the answer is yes, you can use it in any other application.
Yes, I understand. Okay, thank you.
Thank you very much.
Is there any other question for other listeners?